So, welcome to lecture series. Today we are going to prove the primary decomposition theorem. In last time we have seen using this theorem, if a linear operator defined over a finite dimensional vector space and the vector space is defined over an algebraically closed field capital F, then the operator T can be written as sum of a diagonalizable matrix and a nilpotent matrix space. But primary decomposition theorem will talk about bit more generalized way. So, here the field is not necessary to be an algebraically closed field. I mean to say the minimal polynomial may not be product of linear factors. So, let us quickly recall what is the primary decomposition theorem. The statement of the theorem is like this: say T be a linear operator defined over a finite dimensional vector space V over the field capital F, and let P be a minimal polynomial of T such that P equal to P1 power R1 into P2 power R2 and Pk power Rk, where Pi are monic irreducible polynomial over the field capital F and Ri are positive integers. Let Wi be the null space of the operator Pi power Ri T, then the polynomial operator Pi power Ri T, then V will have direct sum decomposition of W1, W2, Wk, where each Wi is invariant under T. So, this two information will say that the identity operator can be written as sum of some projection operator E1, E2, Ek type, and third one, if Ti is the restriction of T on the Wi, where Wi is the null space of Pi power Ri T, this operator, then the minimal polynomial of Ti is Pi power Ri. So, let us prove one by one. First I will show that we shall show that there are k projection operators on V such that the identity operator is equal to say E1 to Ek such that I equal to E1 plus E2 plus Ek. So, first let us prove this one please, and then I will show that the space having direct sum decomposition please, and the range of the each Ei I will show that is a Wi, range of Ei is Wi. So, we shall show first this one. Given P equal to P1 power R1 into P2 power R2 into Pk power Rk, define Fi equal to P by Pi power Ri. So, Fi is the polynomial when P is divided by Pi power Ri. When this factor is taken out, so that will basically Fi. So, it will be I equal to 1 to k. So, then the GCD of F1, F2, Fk will be certainly equal to 1. So, I can say that F1, F2, Fk are relatively prime, they are relatively prime polynomial pairs. So, in number theory there is a results if the GCD of if F1, F2, Fk are relatively prime, then there exists G1, G2, Gk such that F1 G1 plus F2 G2 plus Fk Gk equal to 1, when this F1, F2, Fk are numbers. But this is also true over the polynomial field theory also, that since F1, F2, Fk are relatively prime, so there exist k polynomials G1, G2, Gk such that G1 F1 plus G2 F2 plus Gk Fk equal to 1. This is a classical results. So, I have utilized that results, that when the polynomial F1, F2, Fk are relatively prime and GCD equal to 1, then there exists k polynomial G1, G2, Gk such that G1 F1 plus G2 F2 plus Gk Fk equal to 1. So, this implies if Hi equal to Gi Fi, I can write down that 1 equal to H1 plus H2 plus Hk. So, this implies the identity operator can be written as H1t plus H2t plus Hkt. So, we are getting a polynomial operator H1, H2, Hk such that sum of this polynomial operator equal to identity operator. Claim each Hj is a projection operator. So, if I multiply Aj to the both side of the star, we have Ajt equal to sigma Ajt into Hit, I equal to 1 to k. See, note that for I not equal to j, your Aj and Hi equal to what? This is equal to, we have your Fj, Gj and Fi, So, this implies P divides Hj, Hi, P divides Hj, Hi, because in Fj Pj power Rj is missing, but which is in the Fi. So, P divides Hj into Hi. So, this implies Hjt into Hit equal to 0 operator, because Pt that minimal polynomial operator, then Pt will be 0. So, Pt is a factor of Hjt into Hit. So, Hjt into Hit must be equal to 0 operator. Okay. So, this implies that Hjt equal to, I will simply will have Hj square t. So, this implies Hj is a projection, it satisfies the definition of the projection. So, this one please. So, I have I as a sum of projection operators. So, if I consider for Ej is equal to, if I consider Aj t, then we have identity operator is equal to E1 plus E2 plus Ek, where Ej equal to Ajt. Okay. Now, I want to show that range of Ajt is Wj. Let alpha belongs to range of Ajt. So, this implies since Aj is a projection operator, so alpha will be equal to Ajt alpha. So, this implies Pj Rj t when it is operating on alpha, that is equal to Pj Rj, this operator, into Ajt and alpha. So, you see that Pj Rj t when operating on alpha, I am getting like this, but this is equal to what? This is equal to 0, since P divides Pj Rj and Aj, since P divides Pj Rj into Aj, so therefore, I will have Pj Rj of t when operating on alpha will be equal to 0 please. Okay. So, this implies alpha belongs to null space of Pj Rj t, that is equal to Wj. So, this implies range of Ej is subset of Wj. Now, I want to show it other way. Let alpha belongs to Wj. This implies Pj Rj t operating on alpha equal to 0. So, this implies Hit operating on alpha equal to 0 for I not equal to j. Since Pj Rj divides Hi for I not equal to j. So, that is why Hit operating on alpha will be also equal to 0. So, this implies, see, alpha belongs to, I have taken Wj. So, alpha belongs to V also. So, alpha which is equal to, we have H1 t alpha plus H2 t alpha plus Hk t alpha, each of them are 0. So, this will be basically equal to Aj t alpha. Except for Aj. So, this implies alpha belongs to range of Aj, which is I am denoting as operator Ej please. Okay. So, this implies null space of Pj Rj of t is a subset of range of Aj. So, range of Aj is exactly equal to Wj for j equal to 1 to k. So, we have seen that there exists k projection operator H1, H2, Hk or E1, E2, Ek such that identity operator is equal to E1 plus E2 plus Ek, and Wj is the range of Hj please. Since Hj is a polynomial, is a polynomial operator in T, so T must commutes with HJT, because these are all polynomial in T. So, if I multiply left hand side or right hand side of the T, it will be remain same. So, T into HJT must be equal to HJT into T. So, this implies since T commutes with the each projection operator, so by previous results Wj must be invariant under T. In previous result we have seen that if the projection operator and each projection operator is commutes with the operator T, then only we will say that the each Wj will be invariant under T. So, using that results I can immediately say here that Wj must be invariant under T. So, we have seen here the linear operator T whose minimal polynomial is product of like p1 power r1 to pk power rk introduces k projection operators h1, h1t, h2t or hkt or e1, e2, ek such that I equal to e1 plus e2 plus ek, and the range of each ei is wi, which is invariant under T. So, therefore, T can be written as direct sum of its restriction operator T1, T2, Tk on W1, W2, Wk. So, T must have direct sum decomposition of T1, T2, Tk, where Ti is restriction of T on Wi. So, you see that the space is also having direct sum decomposition of invariant subspaces W1, W2, Wk, and T is also having direct sum decomposition of operator T1, T2, Tk. Finally, we have to show the minimal polynomial of each Ti is pi power ri. We have pj power rj t, when this polynomial operator, when we have when pj rj t operates on Wj, we have pj rj t equal to 0. So, this implies pj rj tj equal to 0. When pj rj t operates on Wj means restricted to Wj, so it is basically Tj. So, pj rj of Tj equal to 0. So, this implies if T denote minimal polynomial of Tj, then T divides Pj Rj. We have T into Fj, T into Fj is a polynomial such that T T Fjt, this is when operating on any alpha belongs to V, so this will be equal to 0. Why? Because alpha will be equal to, I will have H1t or U1, this one plus H2t alpha plus Hkt of alpha please. So, I will have a component over the like alpha 1 plus alpha 2 plus alpha k type. So, this alpha will be, each alpha will be annihilated by pi power ri of t, because alpha is coming from Wi and the Wi is the null space of pi power ri of t by this one for I equal to 1 to k except I equal to j, and alpha j will be annihilated by pj power rjt, because pj power rjt having null space as wj. Null space as wj. So, this implies T of capital T, I have taken alpha j will be annihilated by small t t please. Small t t, because alpha j will be annihilated by small t t, because alpha is a element in Wj and T of Tj, we have already mentioned that T of Tj equal to 0, because T is the minimal polynomial of Tj. Since T is the minimal polynomial of Tj, so therefore alpha j will be annihilated by T of capital T. This implies P must divide T into Fj. Since P is the minimal polynomial, for T, and we see that for any element alpha belong to V is annihilated by T into Fj of capital T. So, this implies P must divide the polynomial T into Fj. So, this implies P equal to what? Pj power rj into Fj must divide T into Fj. So, this implies Pj power rj must divide small t, small t means the polynomial please. So, in one place we have seen that T divides Pj power rj, in another case Pj power rj divides P. So, these two informations together says that so T must be equal to Pj power rj. So, minimal polynomial of Tj is Pj power rj. So, this is the proof of these theorems, and you will see these theorems can be used in variety of places which we will discuss in our next classes please.